Welcome to the session on centrifugal compressor. So this is the first session on centrifugal compressor. Centrifugal compressors actually belongs to the category of rotary compressors. So rotary compressors are classified to centrifugal and axial compressors. So of which we will confine our discussion to centrifugal compressors in this session. So the main components of a centrifugal compressor are actually, it is just the similar one that of a centrifugal pump. It will consist of a rotary element which is known as the impeller. This is the rotary impeller, which is a rotating component, and the second component is a diffuser. You can see here a diffuser. A diffuser is a stationary component. So two components, basically a rotating component which is known as the impeller and the stationary component which is known as the diffuser. Impeller is actually a rotating wheel with a number of blades, and diffuser is a stationary element which is an increasing cross-sectional area. You can see increasing cross-sectional area here. And the air enters the impeller at the eye of the impeller axially. That means perpendicular to the plane of the paper here. This is the eye of the impeller. This is the impeller. The air will be entering into the impeller axially like this. Then the impeller will be turning and air will pass through the passages of the impeller, then moves on to the diffuser. Diffuser is an increasing cross-sectional area. So the function of the centrifugal compressor will be to provide air with a higher pressure ratio. So work is done by the impeller on the air, by which air gains internal energy and which is manifested as a rise in kinetic energy and pressure energy. The application of this centrifugal compressor will be in a turbojet, turbofan, small gas turbines, etc. So what happens? At the eye of the impeller, the air will be sucked in, and as the impeller is rotating, the air moves through the impeller through the passages of the impeller, and a centrifugal head is actually developed. So that centrifugal head will cause the kinetic energy and pressure energy of the air to increase in the impeller. From the impeller, it moves on to a gradually increasing cross-sectional area diffuser. Again, as the area is increasing, the dynamic pressure is converted to static pressure again. So the total pressure rise in static pressure is actually obtained both from impeller and from the diffuser. Then it is taken downstream where it is delivered to the required applications. So if we analyze the inlet and outlet velocity diagrams, it will be like this. So the impeller is actually, the air is entering into the impeller axially, and the shape of the impeller is such that the air will be leaving the impeller radially. So the inlet velocity triangle is such that as air is entering axially, you can see here the air is entering axially, so it will be in a direction perpendicular to the rotation of the impeller. So the velocity, this will be the velocity of air entering axially into the compressor impeller. So V1 is at alpha is at 90 degrees. So V1 has got two components. V1 will be equal to Vf1 here, as it is alpha is 90, Vw1 will be equal to 0. So this is the tangential velocity. So the relative velocity component should be like this. So this is the inlet velocity triangle. V1 is at 90 degrees, alpha is equal to 90 because the air enters the impeller axially. It is at 90 degrees to U1, which is the tangential velocity of the impeller. So the relative velocity component will be at an angle theta. The outlet velocity triangle, as I have already mentioned, the shape of the impeller is such that the air after entering will move through the impeller passages and leaves the impeller radially to the diffuser. So this is the impeller and it actually radially leads to the diffuser. So that means VR2, as the air is leaving radially, VR2 will be 90 degrees. So VR2 is at 90 degrees. So this is U2 and this is V2. So here VR2 is at 90 degrees. So V2 has got two components. That component is one is VW2 and here VR2 is equal to VF2. So that means here the tangential velocity U2 and the peripheral velocity at the outlet U2, the peripheral velocity at the outlet U2 and the tangential component of velocity both are equal. U2 is equal to VW2. So if you find out the energy per mass imparted by the impeller on the air, it will be by momentum equation. Work done is equal to torque into angular velocity. By applying that equation, which is same as that in the case of a centrifugal pump, it will be equal to VW2 U2 minus VW1 U1. So here we know that VW1 is 0. VW1 is 0. So this term cancels off. So energy imparted by the impeller will be equal to VW2 U2. VW2 U2. But here VW2 is equal to U2 as VR2 is at right angles. Air is leaving the impeller radially. So energy per unit mass will be equal to U2 square. Very important. So we have derived an expression for the energy imparted by the impeller or the work done by the impeller on the air, which is equal to U2 square. But there is a phenomenon known as slip, very important. Actually, the theoretical discharge or the theoretical energy, it is not theoretical discharge, but theoretically the work done is theoretically equal to U2 square. But there is by a phenomenon known as slip, some energy is lost inside the impeller. And what is that phenomenon? It is actually not because of the viscosity of the fluid flowing through the impeller, but as the impeller is rotating and when the fluid passes through the passages of the impeller, the pressure in the leading side of the impeller, increases and the pressure in the back end of the impeller decreases. So this is because of the rotation of the impeller and as the air flows through the impeller passages. And it is not because of the viscosity of the air. Even if the fluid is having no viscosity passes through such a condition, this slip will occur. So when a fluid passes through the impeller and if the impeller is rotating that fluid, then on the leading side of the impeller, a positive pressure is developed or the pressure increases, and on the back end of the impeller the pressure decreases. So what happens is that this will cause a circulating motion locally near the impeller. This will happen in each and every impeller. So this will cause some energy reduction. So slip will reduce the energy imparted by the impeller. So this will, because of this, the velocity of the fluid, will not be uniformly distributed in these passages. In fact, it will be less here and it will be increasing to this side. So that means a skewed distribution of velocity will be there. So if this is the passage, you can see here I have made it as a skewed distribution here. So from the if you draw it here, the velocity will be lower at this end and it will be increasing gradually to this end. That means the velocity distribution is a skewed one. So this phenomenon is known as slip. And the effect of the slip is that the velocity triangle will change from this condition of VR2. Here you can see that theoretically VR2 is at 90 degrees because the air is leaving the impeller radially. But because of the slip, that component VR2 is no longer 90 degrees. It is no longer radial, but VR2 is making an angle theta. So that means the effect is that the VW2 will be less than U2 here. In actual case, because of slip, VW2 will not be equal to U2, it will be less than U2. That means the energy per mass will be equal to VW2 U2 and it will not be equal to U2 square because VW2 is less than U2. So we have to introduce a term known as slip factor, which is equal to VW2 by U2, so that energy per mass is equal to not equal to U2 square but a slip factor into U2 square. So because of slip, the effect is that the energy per unit mass is not equal to U2 square but it is equal to VW2 U2, or it is equal to sigma U2 square, where sigma is known as the slip factor. So you can have an expression for slip so that we can analyze what is the effect of the slip on the performance of the compressor. So sigma is equal to 1 minus 0.63 pi by n. This is an expression for sigma, where n is the number of blades. So what happens when n increases? When n increases, this term will increase. This term will decrease. When n increases, this term will decrease so that this value will increase. So it will be much closer to 1. That means when n is becoming greater, when the number of blades are increasing, sigma increases such that when n is infinity, sigma is equal to 1. So by increasing the number of blades, we can reduce the effect of slip. Understand? So energy per unit mass is equal to sigma U square. But we have to introduce another term known as power factor, because this much energy sigma U2 square will not be available because of frictional losses, mechanical losses, disk friction, mechanical losses, windage losses, etc. So sigma U2 square will not be imparted to the liquid because of the frictional losses. So another term is introduced which is known as psi is equal to power factor. So energy per unit mass is equal to psi sigma U2 square. Psi sigma U2 square. This is the formula for energy imparted. Okay. So these are the formulas. Energy imparted by the impeller or the work done per kilogram is equal to VW2 U2. So theoretically VW2 is equal to U2. So you can say that it is equal to U2 square. But if you consider the slip factor, the phenomenon slip, then it is equal to sigma U2 square. And if you consider the frictional losses, the mechanical losses, then another factor which is known as power factor, psi sigma U2 square. Now we will derive another expression for this energy imparted by applying steady flow energy equation. But before moving on to that, we have to be familiar with two terms. One is static pressure and another is stagnation pressure. And what is static pressure and what is stagnation pressure or total pressure? Stagnation pressure is also known as total pressure. For that, we may consider a fluid at rest. This is a fluid at rest. Consider a point here, and what will be the pressure experienced by this point of the fluid? It can be measured by a piezometer, and it will be equal to rho gh or rho gh1, the height from this point to this level. So the pressure that pressure is known as static pressure. The pressure experienced by the fluid at rest at a particular point is known as the static pressure at that point, which is equal to rho gh. H is the height of the point, that is known as static pressure. And when a fluid is moving with a velocity v, like here, let this be a stream of fluid and it is moving with a velocity v. And if you find out, consider a point 1 here, and if you find out the static pressure, it will be equal to rho gh itself, rho gh itself. But because of the velocity of the fluid, there will be a kinetic equivalent of pressure and temperature for that fluid. When the velocity of the fluid is considerably high, this kinetic equivalent of pressure or temperature will be a considerable amount. For example, it may be up to 15 to 20% of the total energy of the fluid. So we cannot neglect that kinetic equivalent. But when the velocity is less, as in the case of centrifugal pump, we haven't considered these stagnation properties. But in the case of a compressor, as the velocity of air inside the compressor is very high, because the RPM of the centrifugal compressors are up to the order of say 20,000 to 30,000. So the velocity of the fluid or air is considerable. So the kinetic equivalent of the properties will be significant. So we have to consider the kinetic equivalent part of the properties also. How can we find out the kinetic equivalent of pressure and temperature? For that, we will consider a pitted tube here, and we can find out the kinetic equivalent part by considering that the fluid is made to stagnant at a point. At this point 2, the fluid is made to stagnant. That means let the velocity of the fluid be 0. So, and applying the Bernoulli's equation between point 1 and 2, we can obtain here as P1 by rho plus V1 square by 2. We are neglecting the potential component. It will be equal to P2 by rho plus V2 square by 2. So what is the assumption we made? We have made the velocity of the fluid at point 2 to 0. So then what happens? This V2 square is equal to 0. That means P2 by rho is equal to P1 by rho plus V1 square by 2. That means P2 is equal to, by dividing with or multiplying with rho, we get P2 is equal to P1 plus rho V1 square by 2g. That means the pressure here, the total pressure here will be equal to the static pressure plus rho V1 square by 2g, which is the kinetic equivalent of pressure. So stagnation pressure P2 for the fluid is equal to the static pressure experienced by the fluid plus the dynamic pressure. Stagnation pressure is also known as total pressure. So total pressure is equal to static plus pressure plus dynamic pressure. That means it is equal to P1 plus rho V1 square by 2g. Similarly, we can find out the static temperature also, or stagnation temperature also. Again, the idea is same. We are considering a stream of fluid. Let the stream consider a point 1, and we are making the velocity 0 by making the passage to a very divergent section. So applying the steady flow energy equation between 1 and 2, we are considering that no external heat transfer or work transfer takes place. Then the steady flow energy equation will become H1 plus V1 square by 2 plus Z1 is there. We are neglecting potential energy difference also. Then it will be simply H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So V2 is considered to be stagnant, so 0. So H2 is equal to H1 plus V1 square by 2. What is H1? This is H2 means this is the stagnation enthalpy. So stagnation enthalpy is equal to static enthalpy plus the kinetic component of enthalpy, energy. So what is H is equal to? H is equal to CPT. So we can write this equation as CPT2 is equal to CPT1 plus V1 square by 2. That means T2 is equal to T1 plus V1 square by 2 Cp. So the static temperature is stagnation temperature is equal to static temperature plus V1 square by 2 Cp, which is the kinetic equivalent of temperature. So this is the total pressure or stagnation pressure. This is the total pressure or stagnation pressure, which is equal to static pressure plus rho V1 square by 2g. This is the stagnation temperature, which is equal to static temperature plus V1 square by 2 Cp. So if we got the idea of stagnation temperature and pressure, now we will move on to derive the work done, another expression for work done by applying steady flow energy equation. So if we apply the steady flow energy equation, we will get the energy per another expression for energy imparted per mass or the work done per kilogram by the impeller. For that, we will consider 3 sections. Section 1 is impeller inlet, section 2 is impeller outlet, and section 3 is the compressor outlet or the diffuser outlet. Okay. So if you apply this steady flow energy equation between 1 and 3, that means at the inlet of the compressor and outlet of the compressor, it will be H1 plus V1 square by 2 plus Z1G plus W is equal to H3 plus V3 square by 2 plus Z3G plus Q. And we are considering that the process inside the compressor is isentropic, so Q will be 0, no heat transfer. Then the potential difference can be neglected. Then H1 plus V1 square by 2 plus W is equal to H3 plus V3 square by 2. So what is W? W is equal to H3 plus V3 square by 2 minus H1 plus V1 square by 2. That means this is the stagnation enthalpy at 3 and this is the stagnation enthalpy at 1. That is expressed as H03 minus H01. So work done, we have got another expression for work done which is equal to H03 minus H01. Okay. So in terms of temperature, it will be Cp into T03 minus T01. T03 minus T01. So that can be equal to Cp into T02 minus T01 because T03 and T02 are the same. Why? So the energy impartation, the imparting of energy or work is done by the impeller alone. So additional energy is imparted to the fluid only at the impeller. So during the process in the diffuser, only conversion of dynamic pressure to static pressure take place. No additional imparting or work done is there. So T02 will be equal to T03. Only conversion is there, no additional energy is supplied. So T03, the total temperature at 2 and 3 are the same. So we can write Cp T03 minus T01 as Cp T02 minus T01 also. So this is another expression for the work done. Okay. Now, considering the process from 1 to 3 as adiabatic process, considering the process inside the compressor as adiabatic process, P03 by P02 is equal to T03 by T01 all raised to gamma by gamma minus 1, which is the adiabatic equation for pressure ratio. So what will be T03 by T01? It will be equal to P03 by P01 all raised to gamma minus 1 by gamma. So writing the above expression, Cp is equal to T03 minus T01 and rearranging it with taking T01 outside, we can write it as Cp into T01, T03 by T01 minus 1. So Cp into T01, what is T03 by T01? It is P03 by P01 to raised to gamma minus 1 by gamma minus 1. So this is another expression for work done. So we can have different expressions for work done in the compressor. So this is an expression in terms of the stagnation temperature at the inlet and the pressure ratio of the compressor. So these are the expressions which we have derived. First one is VW to U2, and theoretically VW2 is equal to U2 as the air is considered to be discharging radially from the impeller. So it is equal taken as U2 square. But because of the occurrence of the phenomenon slip, we have to consider a slip factor which will be equal to sigma U2 square if you consider the slip. And if you consider the frictional factors also, then it will be a power factor also is introduced, psi sigma U2 square. So this psi sigma U2 square can be equated to this equation H03 minus H01, or can be equated to Cp into T03 minus T01, or can be equated to this equation Cp T01 P03 by P01 to raised to gamma minus 1 by gamma minus 1. So these are the expressions for work done. So with this we will wind this session, and in the next session we will find out an expression for the pressure ratio in terms of the tangential component or the peripheral velocity of the impeller at outlet.